Hi, my name is Chris Mason, and today we're going to talk about hardware-accelerated clusters, so using GPUs to accelerate cluster technology. So some of the challenges that we've heard people express about their data centers or their large network of clusters range from space, power, and performance. And this slide actually shows a bunch of actual quotes of some of our users and some of the potential customers that we work with who are looking to improve on their computing configurations. So in terms of a space, absolutely, if you're downtown in an office building and there's literally no physical space left for any of your hardware, that can really be an issue when you're trying to grow your computing center and have higher throughputs on your data simulations. Same with rack-mounted solutions if you've run out of space there as well. Power and energy is becoming one of the biggest challenges. In particular, high-performance computing often requires clusters that take a lot of power, and to the point where the amount of hardware that you've added to your system is at the maximum of what the circuits or transformers can support. In some cases, as one of these quotes comments on here, the electric utility company may actually be unable to service your facility with more power. And cooling as well. Being able to cool all of this infrastructure can take a large amount of energy and power, which it just may not be available to the organization. And performance, on top of a smaller power footprint and space footprint, we want everything to go faster. We want better performance, and these are the challenges that people face today in their data center. So what we're going to talk about in this webinar specifically is we'll start talking about how we can use GPUs to improve the performance in conjunction with CPU servers. How can we get better performance and a better power and space footprint? We'll take a look at GPU clusters themselves, what they look like at a high level in their architecture. We'll also talk about some product solutions that solve this problem and the evolution of GPUs going forward, or the evolution of clusters, that is, going forward. So to begin, if we take a little bit of a look at a history of picking one specific field, the modeling of electromagnetic objects, in particular, in this case, a cell phone. Previously, antenna engineers would be restricted to being able to model just the antenna itself, by itself, on a single PC or workstation, and this was common practice. But of course, once you add the phone or the handset part of the phone to the antenna, it changes the performance significantly. So naturally, the design path began to make more complex models. In doing so, the computation intensity that was required also increased. So 5 to 10 years ago, they started modeling the cell phone by itself, but you required an accelerated workstation to do so, or to get an accurate representation of that model. Today, again, obviously the head, or in some cases the hand or the positioning of the phone, will also influence the antenna signal. So you need even a more complex model. Now you need a model that not only includes the phone, but also the head as well. And again, computing power growing exponentially as the size of the model grows with it. The way one would solve this is in a time-efficient manner, is to use a workstation that has multiple accelerators on it connected to a PC. And if that isn't enough, we want to see how our cell phone and our whole bodies behave electromagnetically inside a car, for example, or inside an aircraft, or on a boat, for example. So again, the scale or the order of magnitude of sizes is exponentially increasing. And how do we tackle this? With a cluster of GPUs, which is again what this webinar is discussing. So why build a GPU cluster? Well, from the last example there in the antenna world, you become memory limited in the sense that you need a supercomputer to compute all of these problems. Other problems that would occur would be, say, in a reconstruction sense, from a biomedical imaging perspective. Let's say you were compute limited by the number of reconstructions that you could do in a minute or in a second, for that matter. So if you want near real-time feedback, you would need something that isn't compute limited, which your current CPU workstations may be today. And then on top of that, if we take a look at a seismic processing job, again, a large-scale, seismic job that might be run in a geologically challenging location, say in the North Sea or something along those lines, you'd find that you have thousands of cores, but you start to you need thousands of cores to scale to this problem, but you can't get data to them fast enough, meaning your memory bandwidth limited. And that's where a lot of HPC problems will run into a bottleneck. So what is a GPU cluster and what does it consist of, now that we've talked about the need for why one might want one of these? So if we start at the upper left corner, a GPU cluster will typically have a head node. This is a CPU node that manages the cluster, controls scheduling, resource management, things like that. Inside the cluster itself, if we're moving down to the left, the GPU cluster itself, each node is a heterogeneous node, meaning that it consists of both a CPU host as well as a GPU accelerator that work together. And the idea is that you need the CPU host to drive the GPUs, to drive the acceleration. What else do you need? You'll also need some software. So in the upper right-hand corner, for example, our libraries actually work on clusters, and that actually is what distributes and delivers the parallelization to all these nodes. You'll need some interconnect, so a high-speed interconnect like InfiniBand or Gigabit Ethernet to connect from node to node to minimize latency and bandwidth when you have to exchange information between the two nodes. And then you'll also need the physical hardware, including the rack, Ethernet cables, and the power to run these. So in an architectural diagram of this cluster, the way it works is you've got a CPU host shown there on the left, and it's going to be connected via a PCI Express cable or an extender cable out to a GPU server. In this case, we're using one of the relatively old S870s as an example. The processing or the job will be distributed across the PCI Express into the Tesla servers and to the GPUs. When you need to communicate between node to node, you can see the line extending to the bottom of the page. You would use, again, your high-speed interconnect, such as InfiniBand, also connecting to a PCI Express slot. So you do need to make sure you have enough PCI Express slots in your host to be able to support this cluster. In terms of the library application platform itself and the way Acceleware provides the solution, what we do is we interface with existing software applications. We provide an API to our library that handles the parallelism of the algorithm across whatever hardware happens to be underneath, whether that's a cluster or a multi-GPU configuration. So as shown on the left there, the hardware that's underneath, it becomes platform independent. The API won't change depending on what hardware's underneath. So you can use multi-core CPUs, GPUs, you can use clusters, any of the future evolutions, whether it's FPGA or I guess in Intel's case, not so much a Larrabee now as a Knight's Ferry or things like that. On the right-hand side, our expertise actually comes in optimizing for these platforms. So understanding CPU and GPU optimization techniques, including understanding how to program for a multi-core or massively multi-core processor, understanding cache optimizations and vectorization of codes, understanding how to use CUDA or OpenCL for GPUs, and how to use multi-GPUs as well as a cluster of GPUs, including MPI. So your performance of your algorithm itself is going to depend, will be highly dependent on the nature of your application and problem. So some examples of a compute limited, meaning you're limited by the number of gigaflops in the system, include things like filtered back projections and n-body simulations in the areas of molecular dynamics and scanner image reconstruction. In those cases, excuse me, you'll be limited by the amount of processing that you have available to you, compared against a memory bandwidth limited case such as reverse time migration or the finite difference time domain technique, things that are used in seismic data processing or electromagnetic modeling, where you're limited by how fast you can bring information from the GPU memory or CPU memory for that matter into the processor itself. And the third class of problems include where you're I/O limited, meaning you're limited by disk access transfer time, so getting data to and from a disk. Again, that applies to seismic data processing, MRI image reconstruction. And in a lot of these cases, all of these problems are going to be memory limited. You're going to be limited oftentimes by how big of a simulation you can fit on a CPU or GPU by memory. So this slide here actually shows some performance metrics for a cluster of GPUs that we use to model a simple electromagnetic structure. And what it shows is scaling across the simulation size. So as the simulation size increases, the throughput also increases as well. So if we compare that reference against a 32-core CPU cluster, this is an 8-node cluster that we're comparing it against, what you actually see is quite a bit better performance in terms of throughput as you increase the number of nodes of your GPU. What it also potentially suggests is how to choose an appropriate size of GPU, or a size of your cluster specifically for your GPU. So if your simulation, say, occupies, it would be 1,000 megacells or a gigacell, around 8 nodes, you would have sufficient number of GPUs to solve that problem. You see with the 4-node GPU solution that the performance starts to tail off around 800 megacells. That's because you're running out of GPU memory. And of course, with newer parts such as the S1070, which we support, you'll actually see that these performance curves will be extended much further out as the amount of memory per card is much higher. Also of interest is a much larger CPU cluster, so around 80 nodes. And again, you can see that an 80-node cluster performs, say, roughly about 2.5 times slower than an equivalent 12-node GPU cluster. So again, back to the space savings, you can see that you're saving a lot of space as well as getting performance by doing or by considering to use a GPU cluster. And then the 300-node cluster, again, also in the same ballpark of simulation size that's run. Again, better performance, but still quite a bit less than the 12-node GPU cluster. So both on cost, power, and space, the GPU cluster can be a better choice. And finally, the Blue Gene processor as well, from IBM with 4,000 processors, fits somewhere on the left-hand side there. So it's definitely a benchmark we're proud of in the sense that a 4-node GPU cluster can beat 4,000 processors from a Blue Gene conventional CPU architecture. So addressing data center challenges, again, we mentioned this at the opening of the presentation, space, power, and energy, and performance. Basically the conclusions from the last slide. You can get more than double the performance in less than half the space. Compare a 12-node heterogeneous cluster to that 80-node traditional cluster. Significantly less power and energy used, which obviously improves your thermal footprint and makes cooling a lot easier as well. And performance is on par with world-class supercomputers. So hardware acceleration in the GPU sense scales very well into the data center. Our cluster solution allows you to work with cluster-enabled algorithms that are software and library support that are integrated into a lot of your favorite software tools and algorithms that you use. We support all the way from NVIDIA Tesla G80 GPU accelerators through the latest Fermi architectures, so S2070s, C2050s, and C2070s. Supports all different types of hosts and supporting hardware, again, with the caveat that there's enough PCI Express, which in most cases there will be. We support 4, 8, 12, and 16 node configurations, and we have done on-site installs for a lot of these clusters, and we're very familiar with being able to set them up. So an Acceleware cluster is a solution, or can be a solution, to your data center problems. So the evolution, the platform includes all the way from 10 series hardware to the, as I mentioned, the Fermi architectures, with plans to expand that to even further onto AMD GPU hardware, as well as Intel high performance parts, including Knights Ferry, Knights Corner. So you're going to see more algorithms and applications that are clustered enabled from Acceleware in the near future. And we're continuing to evolve our products and service to make it easy for you, the end user, to continue to benefit from all of the evolution of the hardware and GPU technology advances. So in conclusion, thanks for your attention. If you have any further questions or comments, you can always contact us. You can contact me directly at chris.mason@acceleware.com. Thank you.